Imagine a species of humans, intelligent, tool-using, social, crossing open water to reach an island sometime in the deep past, and then, over thousands and thousands of generations, slowly, quietly, getting smaller. Not metaphorically, not culturally, physically smaller, their bones, their brains, their entire bodies shrinking down until they stood about as tall as a modern 3-year-old child. That actually happened. On a single island in what is now Indonesia, a human species appears to have miniaturized, and the world didn't find out until 2003. The island is called Flores. It sits in the eastern part of the Indonesian archipelago, a narrow strip of volcanic land surrounded by deep ocean channels that have never been crossable by walking, not even during the ice ages when sea levels dropped dramatically and much of Southeast Asia was dry land. Flores stayed an island, always surrounded by water, always cut off, and apparently that isolation did something remarkable to the humans who ended up there. When archaeologists first pulled the bones from a cave called Liangbua in 2003, they thought they'd found a child. The skeleton was tiny. Then they looked closer. The bones were fully adult. The wear on the teeth, the fusion of the growth plates, the structure of the skeleton, all of it said adult. A fully grown human being standing roughly a meter tall, with a brain about the size of a grapefruit. They eventually named the species Homo floresiensis. The popular press immediately called them something else, the hobbits. Now that nickname stuck for a reason. There's something almost mythological about the idea that a small, clever, tool-using human species was quietly living on a tropical island while the rest of the world was doing what humans do. And the scientific questions that followed that discovery were enormous. How did they get to Flores in the first place? How long were they there? Why did they shrink? What did their lives actually look like? And perhaps most unsettling of all, did they ever meet us? This episode is going to walk through all of that, slowly, without rushing. Because this story deserves patience. It's a story built from fragments of bone, layers of volcanic sediment, stone tools that nobody expected to find, and an ecosystem so strange it sounds invented. Giant storks, dwarf elephants, Komodo dragons, a cave that kept secrets for tens of thousands of years, and the evidence is genuinely uncertain in places. Scientists have disagreed, sometimes sharply, about almost every part of this story. Dating, ancestry, cognitive ability, when they arrived, when they disappeared, whether the shrinking was gradual or fast, whether they were a separate species at all. So rather than pretending we have clean answers, we'll explore what the evidence suggests, where theories compete, and what still keeps researchers up at night. If you're listening to this to help you sleep, that is exactly what this is for. Long, calm, genuinely interesting history that gives your brain something to follow, while the rest of you lets go. So get comfortable. You don't have to be anywhere. Nothing is urgent. Just an island, some remarkable bones, and a mystery that started roughly 50,000 years ago, maybe much longer. Before we go further, I want to know where you are right now. Drop it in the comments. What time is it? And what corner of the world are you listening from? Someone will be in a city I've never heard of. Someone else will be in a time zone while most of their household is asleep. I read these and I love them. The geography of an audience falling asleep at different hours of the same night is its own kind of strange and beautiful thing. Now, let's go to Flores. To understand what happened on Flores, you first have to understand where Flores sits. And to understand that, you have to let go of the map you carry in your head, the one with fixed coastlines and stable continents. Because the world that this story takes place in looked fundamentally different from the one we know. The ground itself was different. The ocean was different. What counted as an island? What counted as peninsula? What counted as dry land you could walk across? All of it was subject to change. Deep, slow, geological change, measured not in years, but in thousands of years, in ice ages and their endings. Start with the big picture. Southeast Asia today is an archipelago, an enormous scattering of islands stretching from the Malay Peninsula eastward into the Pacific. Indonesia alone contains more than 17,000 islands. The Philippines, Borneo, Sulawesi, Java, Sumatra, New Guinea, and then hundreds of smaller islands beyond. From above, the whole region looks like something shattered and scattered across a warm blue ocean. But during the ice ages, when vast amounts of water were locked into glaciers and polar ice sheets, sea levels dropped significantly. at times perhaps 100 meters lower than today. And when that happened, much of what is now shallow ocean floor became exposed land. The continental shelf connecting mainland Southeast Asia to Borneo, Java, and Sumatra rose out of the water and became a landmass so large it has its own name, Sundaland. It was essentially a subcontinent, enormous, forested, connected to the Asian mainland by stretches of dry ground that animals and eventually humans could walk across without getting their feet wet. To the east of Sundaland, the Australian continental shelf did something similar. When sea levels dropped, Australia and New Guinea merged into a single landmass, another giant continent hiding just beneath the surface of what is today shallow sea. That one also has a name, Sahul. But here is the critical thing. Between Sundaland to the west and Sahul to the east, there was a zone that never fully connected. A collection of islands surrounded by deep ocean channels carved not by shallow continental shells, but by genuinely deep water that didn't empty out even when sea levels fell dramatically. This zone is called Wallacea, named after the 19th century naturalist Alfred Russel Wallace, who noticed something remarkable about it. The animals on the western side of this zone were Asian animals, tigers and orangutans and rhinoceroses. The animals on the eastern side were Australian animals, marsupials and strange birds and reptiles found nowhere else. And in between, a scattering of islands where neither suite of animals had fully penetrated. Because crossing those channels, even at the height of an ice age, required something most animals couldn't manage. You had to cross open water. Flores sits in the heart of Wallacea, a long, narrow island, roughly 360 kilometers from end to end, shaped something like a dragon stretched across the sea. It's volcanic, noticeably so. Steep mountain ridges run down its spine, some of them still active, and the landscape has the rugged, folded quality of land that the Earth hasn't quite finished reshaping. The soils are fertile from millennia of volcanic ash. The forests are dense. The terrain is not easy. Deep valleys, rapid rivers, slopes that rise sharply from the coast. And crucially, flora is never connected to anything else. Not to Java to the west. Not to Sumbawa. Not to any other land mass. Even at the lowest sea levels of the most severe ice ages, the channels surrounding Flores remained open water. The Wallace Line, the deepest boundary in this biogeographical puzzle, runs just to Flores' west, which means that anything arriving on Flores, whether plant, animal, or eventually human, had to cross water to get there. There was no other way. That kind of isolation does something specific to evolution. When a population reaches an island and gets cut off, it enters a different kind of selective pressure. The rules change. The resources are finite. The predators may be different from the mainland, or absent entirely. The competitors for food may be different, and the population itself is small, which matters genetically. Small populations evolve faster. Genetic drift operates more powerfully. Traits that would be averaged out in a large continental population can become fixed in a small island population within a surprisingly short number of generations. The results can be dramatic. Islands produce evolutionary experiments you wouldn't see anywhere else. Animals that grew gigantic because there were no large predators to keep their size in check. Animals that shrank because resources were limited and smaller bodies were more efficient. Birds that lost the ability to fly because flight was energetically expensive and there was nothing on the ground trying to eat them. Islands, in the language of evolutionary biology, are natural laboratories, isolated, bounded, running their own long experiments with no outside interference. Flores had been running those experiments for a very long time before any human arrived. The creatures that had managed to reach it over hundreds of thousands of years had all been shaped by it. The stegodon, a relative of elephants, had arrived somehow, probably by swimming, which large mammals can do across surprisingly wide stretches of water. And it had changed on Flores, become smaller, the dwarf version of an already ancient lineage. The Komodo dragon was there, having arrived from Australia or nearby islands, an enormous predatory lizard that found on Flores something it couldn't find everywhere. A place where it could be the largest thing hunting. This was the world waiting, rugged and isolated and strange and old. A piece of land that had been quietly doing its own evolutionary thing for an enormous span of time. And then, somehow, humans entered it. So the question becomes, how did they get there? It sounds simple when you say it quickly. Humans reached Flores. But sit with that sentence for a moment and let it become strange again. Because it is strange. Flores was surrounded by open ocean, not a narrow stream, not a shallow ford you could wade across at low tide, deep water channels stretching for kilometers, with no visible land on the other side. The kind of crossing that requires either deliberate intent and some form of watercraft, or an accident of remarkable improbability, or something in between that we don't yet have a clean word for. Archaeologists working in this region are careful with their language, and for good reason. The evidence is fragmentary. The island is old and volcanic, and the processes that preserve bone and charcoal and stone tools are working against you. Tropical heat and humidity accelerate decay. Earthquakes and eruptions churn the sediment layers that scientists depend on for dating. What survives is a partial record at best, and reading it requires a kind of disciplined humility. You can see what's there. You cannot always be certain what it means. What archaeologists look for, when they're trying to establish that humans occupied a place at a particular time, falls into a few broad categories. Stone tools are the most durable. They don't rot. They don't dissolve. A flaked stone tool, something that could only have been made by a hand with intention behind it, sitting in a dated sediment layer, is about as solid a piece of evidence as this kind of archaeology provides. Then there are cut marks on bone. If you find the bones of animals with precise repeated angled scratches that match the motion of a stone blade removing meat from a carcass, that tells you something was processing those animals, not just gnawing on them opportunistically, but systematically butchering them. And then there are hearths, concentrations of charcoal and ash and heat-reddened earth, sometimes with burned bone mixed in, that speak to deliberate fire use. Fire management is one of the clearest signatures of hominin presence we have. On Flores, all three of these lines of evidence exist. Stone tools have been found in multiple locations across the island, including at a site called Matamengue in the Soa Basin, where the sediment layers have been dated to around 700,000 years ago. That number deserves a pause, not 50,000 years ago. 700,000. Which means the question of when humans first reached Flores isn't a question with one answer. It may have multiple answers, spread across a staggering span of time, involving multiple different groups of hominins arriving, surviving, evolving, and perhaps disappearing and being replaced. The widely accepted arrival date for the particular population that eventually became what we now call Homo floresiensis sits somewhere around 100,000 years ago or earlier, based on the fossil and tool evidence from Liambua Cave and surrounding sites. Some researchers push that figure back further. Others focus on the 50,000-year range for the clearest and most concentrated evidence of occupation. The honest answer is that the timeline is still being refined, and different sites on Flores suggest different moments of arrival and activity. But here's what makes Wallacea so significant in the larger story of human prehistory. Every hominin population that ever reached Flores had to do something that most species simply cannot do. They had to cross open water intentionally or survive being carried across it. And that distinction matters enormously. There are two basic models for how land animals end up on oceanic islands. The first is called sweepstakes dispersal, a raft of floating vegetation, the kind that forms naturally when rivers flood and uproot trees and wash debris into the sea, carries an animal passively across a water gap. It's rare, it's accidental. It doesn't require any capability on the part of the animal beyond surviving the journey, which many don't. This is probably how the stegodon got to Flores, probably how the Komodo dragon's ancestors arrived. Passive, lucky, rare. The second model is intentional crossing. You build or find a vessel. You paddle or you push off or you drift with some understanding of direction. This requires cognitive capacity. It requires planning. It may require communication, coordination, some shared understanding of purpose between individuals crossing together. For a long time, the assumption was that early hominins, the ones preceding modern humans, weren't capable of intentional seafaring. That was supposed to be a modern human achievement, something that came late in the story, bundled with language and art and symbolic thinking. But Flores complicated that assumption, badly, because the stone tools at Matamengue predate any modern human presence in the region by hundreds of thousands of years. Whatever made those tools was not Homo sapiens. It was something older, and it crossed open water to get there. This doesn't necessarily mean those early hominins had boats in any recognizable sense. They might have used bamboo rafts, which can be remarkably seaworthy, and which grow abundantly in this part of the world. They might have crossed during unusually calm conditions, or during events that temporarily reduced the distance between islands. Some researchers have proposed that tsunamis could theoretically carry groups of individuals from one island to another, alive and shocked but intact. It sounds fanciful until you consider that tsunamis in this region are not rare events. They are a geological fact of life. What seems increasingly clear is that Wallacea was crossed not once but multiple times, by multiple populations, at different points in deep time. The region wasn't an impenetrable barrier. It was a difficult one, a barrier that demanded capability and perhaps luck, but one that various hominin groups managed to overcome across an enormous span of time. Each of those crossings would have been, for the individuals involved, the end of one world and the uncertain beginning of another. They would have stepped off a vessel or washed ashore or stumbled up a beach with no knowledge of what the interior held. No map, no precedent, no way of knowing that the island they had reached was about to become something else entirely. A place that would slowly, quietly, patiently make them into something new. Imagine you're walking inland on Flores, away from the coast where the waves hammer the rocks and the salt hangs in the air, up into cooler, greener country. Rice terraces today step up the hillsides, but underneath that modern pattern the land is older, carved by water and time into ridges and valleys and sudden limestone cliffs. In one of those cliffs on the western side of the island, there's an opening, Liang Bua. In the local Manggarai language, the name means cool cave. It fits. Step inside and the temperature drops. Outside, the light is harsh, the sun almost white. Inside, it goes soft and gray, like someone turned the brightness down on the world. Your footsteps change too, from the crunch of dry soil to the muffled thud of dust laid down layer after layer, season after season, for tens of thousands of years. Caves like this are strange places. They're both fragile and durable at the same time. The roofs can collapse, water can carve them into new shapes. But the floors, the places where windblown dust and ash and tiny fragments of bone slowly accumulate, can become time machines. That's because caves are good at doing something the rest of the tropical landscape is bad at, keeping secrets. Out in the open, heat and humidity are relentless. Bones rot, wood vanishes. Even stone tools can be moved, scattered, buried by roots or washed down slopes by sudden rains. In a cave, especially one with a high ceiling and a stable entrance, you have shelter from the worst of it. Less direct rain, fewer temperature swings, fewer scavengers dragging things away. Year after year, particles of dust fall, tiny flecks of ash settle, bits of broken tool, fragments of bone. One storm, one season, one decade at a time, they build up into a stratified archive. That's what drew archaeologists to Liangbua in the first place. Not a rumor of little people, not a legend. Just a practical observation. Here is a large cave, in a region known to have deep human history. If people ever sheltered here, the evidence might still be underfoot. Excavations at Liangbua had actually started long before anyone heard the words Homo floresiensis. Indonesian researchers began digging in the cave in the 1960s, finding pottery, metal artifacts, the usual signs of fairly recent human occupation. People had been using the cave in the last few thousand years as a shelter, a burial place, a temporary home. That alone made Liangbua interesting, but not unusual. Deeper digging came later. In 2001, a joint Indonesian-Australian team returned with a broader question. How far back did human presence on Flores go? The Mataminga tools suggested something very old was happening elsewhere on the island. Liangbua, with its deep floor deposits, seemed like a promising place to search for older layers. If you had walked into the cave that season, you would have seen gridded squares marked on the floor, strings and stakes and measuring tapes. Archaeologists on their knees carefully scraping away thin slices of sediment with trowels and brushes. Every bucket of earth lifted out, sieved. Every fleck of charcoal, every chip of stone, every bone fragment logged with almost obsessive care. Layer by layer, they were literally moving backward through time. In September 2003, about 6 meters down from the modern cave floor, they found something that should not have been there, at least not in the form it took. A skull. That alone is a big deal in archaeology. Complete or nearly complete hominin skulls are rare. Most of the time, you get teeth, a jaw fragment, maybe part of a limb. A skull is a treasure. It holds information about brain size, face shape, the architecture of the chewing muscles, the way the head balanced on the spine. But what the team at Liangbua uncovered was not just a skull. As they continued to excavate, they realized they were dealing with much of an entire skeleton: a cranium, a jaw, vertebrae, ribs, pelvis, arm bones, leg bones, bones of the hand and foot. Enough to sketch, in bone, a whole person. The individual would later be catalogued as LB1, Liangbua Specimen 1. At first, in the dust and low light of the cave, LB1 might have looked like any other set of old human bones. But as they were cleaned, measured, and compared, something about them began to whisper that this was no ordinary find. The skeleton was small, not just a little small, very small. When you reconstruct a skeleton like this, you use known relationships between limb bone length and body height. Every species has its own proportions, but there are patterns. The femur, the thigh bone of LB1, combined with the lower leg bones, told a consistent story. This individual, as an adult, would have stood roughly a meter tall, about 1.0 to 1.1 meters, around 3.5 feet. The pelvis suggested an adult female, not a child. The teeth supported that, worn enough to show years of use. The bones themselves had fully fused growth plates. This wasn't someone who had died before finishing growing. This was someone who had reached their mature size, and that mature size was the size of a human toddler. This immediately raised a simple, almost reflexive question in many minds. Was this just a modern human with a severe growth disorder? There are conditions, like microcephalic dwarfism, that can result in small stature and reduced brain volume. Maybe, some argued, the find was unusual, but not a new kind of human. The skull complicated that suggestion. When the team measured the inside volume of the cranium, they arrived at an estimate of around 400 cubic centimeters. That's in the range of a chimpanzee or the much older hominin Homo erectus infants, and far below the roughly 1,350 cubic centimeters typical of modern humans. Yet the face of LB1 did not look like a chimpanzee. The dental pattern had human-like features. The proportions of the limbs were not a simple match to any known modern dwarf conditions. Some aspects of the wrist, shoulder, and foot bones seemed primitive, more like older hominins than like Homo sapiens. It was a mosaic. Some features that looked modernish, some that looked archaic, all wrapped up in a very small frame on an island that had already hinted at strange evolutionary experiments. By the time LB1 was fully described, there were more bones to compare it with. Additional partial remains from Liangbua, other jaws, limb bones, fragments of individuals, aligned with the same general pattern. Small-bodied, small-brained, with a consistent suite of anatomical traits distinct from both modern humans and known pathological conditions. A picture began to form of not one unusual person, but a population. When the research team published their findings in 2004, they proposed a startling conclusion. These remains represented a distinct human species, unknown to science until that moment. They named it Homo floresiensis, the human of Flores. The response was immediate and intense. News outlets around the world reached instinctively for a comparison that audiences would understand. Small, ancient, cave-dwelling people, discovered on a remote island. The word hobbit leapt from fantasy into headlines. Hobbit humans found. The real hobbit. You can still feel the echo of that first wave of coverage whenever the species is mentioned. The nickname stuck in popular culture, but scientists tend to use it cautiously, if at all. Not because there's anything wrong with Tolkien, but because catchy labels can blur lines the evidence tries to keep clear. For researchers, Homo floresiensis is not a storybook creature. It's a collection of fossils with measurable traits: bone lengths, joint angles, tooth morphology, cranial capacity. Those are the things that matter when you're trying to work out what kind of human you're dealing with, how they moved, how they grew, how they might be related to other branches of the human family. From LB1 and its companions, a few basic facts emerged. Height, somewhere around a meter tall for adults, with some variation, as in any population. Body proportions, relatively short legs compared to the arms, a broad pelvis, and feet that seem long relative to the lower leg, which might have made their gait slightly different from ours, less efficient over long distances, but stable on uneven ground. Brain size, small, on the order of early Homo or even Australopiths, but housed in a skull that shows rearranged internal shape. suggesting that even a small brain can be organized in ways we associate with more complex behavior. There were hints of pathology in some bones. No population is free of illness or injury, but the consistency across multiple individuals made the one sick modern human explanation increasingly hard to defend. All of that, though, was only half the story. The other half lay not in the bones themselves, but in the dirt around them. Where in time did these beings live? To answer that, you go back to the cave, back to those layers of sediment. Each layer is like a line in a diary, but one written by climate and geology rather than by hand. If you can date those layers, you can place the bones and tools within a timeline. At Liangbua, this turned out to be more complicated than anyone had hoped. The original analyses, using a combination of radiocarbon dating on charcoal and other methods like thermoluminescence, and uranium series dating on cave sediments and flowstones, suggested that Homo floresiensis had survived on Flores until around 12,000 years ago. That was astonishing. It would have meant that these small-bodied humans were living alongside modern humans in Southeast Asia for tens of thousands of years, potentially into the very recent past. It made for dramatic headlines. Hobbits lived until yesterday. But as more work was done, cracks appeared in that tidy picture. The problem was stratigraphy, the arrangement of layers in the cave. Burrowing animals, water flow, small collapses of the cave ceiling, all of these can disturb sediments. You can have older material dragged up into younger layers, or young material slipping down into older ones. Unless you untangle that, your dates can end up attached to the wrong events. Over the next decade, teams revisited Liangbua's layers with increased precision. They redated sediments. They mapped the microstratigraphy in fine detail. They tracked exactly which bones and which stone tools came from which tiny slices of the deposit. The result was a revised timeline. The currently favored interpretation places the last clear evidence of Homo floresiensis, bones and associated stone tools, in layers dated to roughly 50,000 to 60,000 years ago. Above those layers, the tools change. The anatomy in the bones, where they appear at all, starts to look more like modern humans. The cave story shifts from one kind of human to another. That revision removed the most sensational version of the tale, but it didn't make Liangbua any less important. If anything, it sharpened the questions. Now, instead of asking whether the hobbits met farmers or Bronze Age sailors, researchers ask a different kind of question. What was happening around 50,000 years ago, on Flores and across the region, that might explain why a distinct, long-lasting island species disappears from the record, just as modern humans are expanding through Wallacea? That's a mystery for later in the story. For now, what matters is this. In a cool cave on a tropical island, the floor turned out to be a layered record of a human experiment no one had suspected. The bones of Homo floresiensis, small and ancient, pulled from meters of dust and ash, forced scientists to rethink some very basic assumptions about what kinds of humans the world has held, and how far evolution can bend a lineage without breaking it. From here, the questions move from discovery to meaning. What exactly made these island humans different from us, beyond their size? What does shrinking really mean in an evolutionary context? And why, on Flores, did smallness become a strategy rather than a disadvantage? If you could lay a modern human skeleton next to LB1 on a quiet table somewhere, the differences would start to speak for themselves. Not all at once, not in a single dramatic flourish, but bone by bone, proportion by proportion. We've already met the headline detail, the height. An adult standing around a meter tall. That alone sets Homo floresiensis apart from most of our species. But it's how that smallness is arranged that really matters. Start at the top. The skull of LB1 is small, but its shape is where the story gets interesting. The brain case is low and long from front to back, more like early Homo erectus, or even some Australopiths than like the high, rounded domes of modern humans. The forehead retreats quickly. There's no towering frontal bone. The brow ridges are there, solid, but not massive, and the face pulls in under them rather than jutting far forward. The jaw is relatively delicate compared to something like a Neanderthal, but it doesn't look quite like ours either. Inside that skull, if you could peel away the bone in your mind's eye and look at the space where the brain once lay, the volume is, by modern standards, tiny, roughly 400 cubic centimeters, about a third of the average for Homo sapiens, about the size of a chimpanzee's brain or a very early hominin. Yet the outer surface of the brain case is subtly remodeled. CT scans and virtual reconstructions suggest that the frontal and temporal regions, the bits of the brain we usually connect with planning, tool use, and social complexity, may have been relatively well developed for such a small package. It's as if evolution took a small volume and rearranged it to squeeze as much function as possible into the available space. Drop your gaze to the teeth. Teeth are conservative. They change slowly, and they carry a lot of information. In Homo floresiensis, the teeth are small, generally in proportion to the skull. The dental arcade, the shape of the row of teeth, leans toward the modern human pattern rather than the U-shaped jaws of some earlier hominins. The enamel thickness, the wear patterns, the way the molars and premolars are shaped. All of these details helped convince researchers that they weren't just looking at a diseased modern human child. The teeth line up with an adult of a small-bodied lineage, not with a shrunken version of our own. Move down the spine, into the pelvis. Here the bones are broad and flaring, giving the lower body a kind of squat solidity. The hip bones look, in some respects, surprisingly primitive, evoking older forms like Lucy's species, Australopithecus afarensis, more than they recall a modern human's pelvis. This isn't just a scaled-down version of our anatomy. It's a different architectural plan. The legs tell a similar story. The femur and tibia, the thigh and shin bones, are short, even when you account for overall height. The lower leg, in particular, is relatively short compared to the foot. The feet themselves are long and slightly flat, with a big toe that lines up with the others, instead of sticking off to the side like an ape's. But the overall structure of the foot bones looks unexpectedly primitive. Some researchers have suggested that a Homo floresiensis footprint would have looked a little awkward by our standards. A long foot, a rolling gait, maybe a step that felt more like a careful shuffle than a springy stride. Up in the arms and hands, the mosaic continues. The upper arm bones are short and sturdy. The shoulders sit a bit higher and more hunched forward than in most modern humans, more like in early Homo or even apes. The wrist bones show shapes that match older hominins, not the fully modern human condition. Some of the finger bones are curved enough to make people wonder how much climbing or vertical scrambling they might have done in their daily lives. Taken one at a time, any of these features might be explained away. Human variation is wide. Diseases and developmental quirks can warp bones into all kinds of unusual forms. But the key here is the pattern. Across the skull, teeth, spine, pelvis, arms, legs, hands, and feet, you see a consistent suite of traits, repeated in multiple individuals from the cave. Small, yes, but small with a particular recipe. This is where the question shifts from what do the bones look like to what kind of human is this? In paleoanthropology, deciding whether a set of fossils represents a distinct species or just a variant of a known one is rarely simple. There isn't a magical percentage where everyone agrees, yes, 12% difference equals a new species. Instead, scientists look for combinations of features, anatomical clusters that hang together and don't overlap much with known variation in other groups. With Homo floresiensis, that process played out in public. On one side, you had the original research team and many of their colleagues arguing, this is a distinct species. Their case rested on the anatomy you've just walked through. The skull shape, the brain size, the primitive elements in the wrist, shoulder, and foot, the broad pelvis, the repeated pattern across multiple specimens. Put together, they said, this isn't what you see in modern humans, even in populations with extreme short stature. It looks like a separate lineage, one that probably arrived on Flores as a larger-bodied hominin, maybe Homo erectus, and then, over many generations, evolved into a smaller form adapted to island life. On the other side, some researchers pushed back. Perhaps they argued LB1 was a modern human with a severe developmental condition. Conditions like microcephalic primordial dwarfism can produce small stature and small brain size. Couldn't that explain the skeleton? The pathology hypothesis came in several versions: microcephaly, Laron syndrome, cretinism due to congenital iodine deficiency. Each idea pointed to real conditions that do affect human growth and bone structure today. If LB1 had one of those, the argument went, then there was no need to invent a new species. The way out of this debate wasn't settled by one dramatic piece of evidence, but by a long, careful process of comparison. Teams measured the LB1 skull against skulls of microcephalic individuals and found important differences in shape. They compared limb proportions and joint surfaces to people with various forms of dwarfism. They looked at the pattern of primitive features in the wrist and foot. In pathology, you often get irregularity. Some bones affected more than others, asymmetries, strange fusions. In Homo floresiensis, what you see instead is regularity. The same small stature, the same limb proportions, the same primitive traits, over and over, in more than one individual. Pathology can shrink a body. It can distort bones, but it doesn't reliably turn the wrists of a modern human back into something that closely resembles early Homo. It doesn't usually produce a neat, population-wide pattern of features that look both ancient and orderly. Most researchers today lean toward Homo floresiensis being a real, distinct species rather than a cluster of sick modern humans. Not everyone agrees. In science, it's rare to get unanimous votes on anything that interesting. But over time, as more fossils and more detailed analyses accumulated, the disease-based explanations have become harder to defend without ignoring chunks of the evidence. Underneath that debate lies a deeper question. What does shrinking really mean? When people hear that an ancient human was only a meter tall with a chimp-sized brain, it's natural to picture an individual who somehow failed to grow. That's how smallness works in our daily experience. A child who is unusually tiny, an adult with a medical condition. The language of hobbits and pygmies doesn't help. It smuggles in modern associations. In evolution, though, shrinking is almost always a population story, not an individual one. Imagine a larger-bodied hominin arriving on Flores. Baby Homo erectus, with a height closer to us and a brain around 800 to 1,000 cubic centimeters. They make the crossing, somehow, and find themselves on an island with limited resources, no big cats or hyenas, and a fauna that's already drifting into its own strange shapes. Dwarf elephants, giant storks, outsized lizards. On an island like that, every calorie matters. Big bodies need more food, more territory, more reliable access to water. Small bodies need less. If predators are scarce and there's no selective pressure favoring size as a defense, being large can be a liability rather than an advantage. Over many generations, individuals who are slightly smaller may survive famines better, reproduce more often, and leave more descendants. That slow statistical advantage accumulates. Millimeter by millimeter, bone by bone, the average size of the population ratchets down. This is what biologists call insular dwarfism, island dwarfing. It's been seen in elephants, hippos, deer, even dinosaurs. On islands with limited resources and reduced predation, large animals often evolve into smaller versions of themselves. Not in a single lifetime, but across thousands of years as natural selection quietly favors the thrifty over the extravagant. If Homo floresiensis is indeed descended from a large-bodied ancestor, then their small stature is probably that kind of evolutionary shrinking, not a mass outbreak of disease. A shift in the average, generation after generation, as the island environment nudged the population toward a more efficient body plan. That doesn't mean the brain simply shrank in lockstep with the body like a scaled-down model. Brain tissue is expensive, metabolically speaking. On an island, you don't want any more of it than you can actively use. One way to think about Homo floresiensis is as a compromise solution. Keep enough brain to manage tools, fire, and social life, but pack it into a smaller, reorganized space. The fossils hint at that rearrangement. Primitive size, but with hints of modern-like internal structure. It's important to keep the uncertainty clear here. We don't have DNA from Homo floresiensis yet, so we can't trace their lineage the way we've done for Neanderthals and Denisovans. We can't say with confidence exactly which species they came from, or precisely how fast their bodies and brains changed. The idea that they're descendants of island-dwarfed Homo erectus is a leading hypothesis, not a settled fact. Some researchers think their anatomy is too primitive even for that, and that they might branch off deeper in our family tree. What is broadly accepted is smaller but solid. That the Liangbois fossils represent a population of consistently small-bodied humans, with a distinct anatomical pattern that doesn't match known modern human variation. That they lived on Flores for a long stretch of time. That their size makes sense in the context of island evolution, where shrinking can be an adaptive response rather than a problem to be explained away. So when we say they began shrinking, it isn't a fairy tale curse, and it isn't one person's misfortune. It's shorthand for a slow, generational drift in body plan, written into bone by the quiet pressures of an island's ecology. On Flores, that drift produced a human who could stand chest-high to you, look up, and still be as fully part of the human story as any of our taller cousins. From there, the question naturally spreads outward. What kind of world shaped them? What predators, what prey, what absences and opportunities turned smallness into a workable strategy? To answer that, you have to step out of the cool cave and into the island itself. The strange community of animals and plants that shared floras with these little humans, and the evolutionary rules that apply when the ocean draws a hard line around a patch of land. Flores isn't just a place on a map. In evolutionary terms, it's a kind of experiment. Not a designed one, nature doesn't plan ahead, but a repeating pattern that turns up so often that biologists gave it a name: the island rule. The idea goes like this, in its simplest form. When animals get trapped on islands, big ones tend to get smaller, and small ones tend to get bigger. Not always, not everywhere. Evolution is messier than any slogan. But over and over, from the Mediterranean to the Pacific, from fossil bones to living species, you see the same broad drift. Dwarfed elephants, giant rats, miniature hippos, oversized lizards. On islands, the middle ground is rare. Things slide toward the extremes. Flores is one of the clearest examples of that pattern. To see why, imagine the island not as scenery, but as a closed budget. On a continent, the ecological accounting has a lot of wiggle room. Huge herds can migrate hundreds of kilometers to follow the rains. Predators can shift territories when prey gets scarce. A drought in one valley might be balanced by better conditions over the next ridge. Energy, food, is patchy, but it's spread across enormous spaces. Islands cut that off. Draw an invisible line of salt water around a chunk of land, and everything inside has to live off what's there. No reinforcements from beyond the shore. No seasonal migration to some distant refuge. If a dry year hits, you ride it out on the spot, or you die. In that kind of world, body size becomes one of the most important variables in the equation. Big animals are walking appetites. They carry a lot of muscle and bone. They can fight, they can run, they can intimidate predators. But every one of those advantages is paid for in calories. A larger heart, a larger gut, more tissue to keep warm, more maintenance, every day. On a resource-rich continent, that cost can be worth it. Being big may win you mates, let you travel farther, let you push smaller competitors aside. If there are also big predators, lions, giant hyenas, saber-toothed cats, size can literally be life-saving. On a small island with no big carnivores and limited food, the math flips. If there's nothing much larger than you that's trying to eat you, the protective value of being huge collapses. You don't need to outrun lions that aren't there. What you do need is to survive the lean season, the bad year, the decade when the fruiting trees don't fruit quite as often, and the herds of edible herbivores are thin on the ground. In that situation, an individual who can do the same basic tasks, walk, forage, reproduce, look after offspring, but on half the calories has a real edge. If they're also slightly smaller and need less space, they can pack into a habitat more densely without exhausting it. Their children, on average, are better buffered against famine. Natural selection is ruthless, but slow. It doesn't decide, it tallies. Generation after generation, smaller individuals leave more surviving descendants. Their genes, the ones that favor reduced growth, altered hormone levels, slightly shorter bones, spread quietly through the population. Over thousands of years, the average size shifts. That's insular dwarfism, island dwarfing. It's not a myth built around Homo floresiensis. It's something first worked out in other species, from other islands, long before anyone knew there was a hobbit on Flores at all. Take the Mediterranean during the Ice Age. When sea levels fell, islands like Sicily and Cyprus were connected and disconnected from the mainland multiple times. Large mainland elephants occasionally wandered across. Then, when the waters rose again, some populations were trapped. Over the next tens of thousands of years, some of those elephants evolved into true dwarves. Not just a bit smaller, but standing sometimes only a meter or so at the shoulder, with skulls and tusks scaled down to match. They're known from fossil sites on islands all across that region. Different islands, different lineages, same basic outcome. Big herbivores turned into pocket-sized versions of themselves. Or look at hippos. On islands like Malta and Crete, fossil deposits preserve species of dwarf hippos that once descended from full-sized river-dwelling ancestors. Trapped on land masses with no big crocodiles, no lions, and limited fresh water, they ended up more like stout pigs than river monsters. Short legs, compact bodies, a smaller animal to feed when the rains failed. Even carnivores show the pattern, although it's more complicated. On some islands, Foxes and mustelids grow larger because they become the top predator, taking on prey that would once have been out of reach for their mainland cousins. On others, they get smaller, probably tracking the downsizing of their herbivorous meals and the reduced size of the land they patrol. There's a mirror process, too. Island gigantism. Small animals like rodents, lizards, or birds can become larger on islands, especially when they move into ecological roles vacated by the absence of big mammals. Think of New Zealand's giant moas, or the dodo on Mauritius, or the massive Komodo dragons prowling the lesser Sunda Islands. All are cases where a smaller-bodied lineage found itself with room to expand, no big competitors, no big predators, and pushed body size upward into unoccupied niches. Flores fits right into this larger picture. By the time Homo floresiensis was living there, the island carried a textbook cast of insular oddities: dwarf elephants called stegodons, giant storks, oversized marabou-like birds, outstretched lizards and varanids that had grown into top predators. A community shifted away from the continental norm, tilted by isolation and the island rule. In that world, a small-bodied human doesn't look like a freak occurrence. It looks like the hominin version of what everything else is doing. The pressures acting on a human population would have been similar to those on elephants and deer, but with some twists. Humans are omnivores. They can eat meat, plants, tubers, fruits, shellfish, whatever the landscape offers. That flexibility helps, but it doesn't erase the basic constraint. There's only so much energy arriving on the island as sunlight, getting turned into plant matter, and moving its way up the food web. Every mouthful a Homo floresiensis took was a withdrawal from a limited account. In that context, a population of tall, heavily built hominins with big brains and big caloric needs would be walking a tightrope. Good years, they'd thrive. Bad years, they'd crash. Their population numbers might spike and then collapse in boom and bust cycles, always flirting with local extinction. A smaller-bodied hominin, by contrast, would ride those waves more smoothly. Imagine two families, identical in every respect except size. One is a meter tall, with a brain of 400 cubic centimeters. The other is, say, 1.6 meters, with a brain around 900 cubic centimeters, like Homo erectus. Give them the same hunting and gathering skills, the same tools, the same social structure. On a cramped island with marginal resources, the smaller family can survive on less meat, less tuber, less fruit. The children need less to grow. The adults can stay active on fewer calories. When a drought hits, or a volcanic eruption chokes the forest with ash, the cost of maintenance is simply lower. Over centuries, that difference plays out as a shift in survival rates. The slightly smaller children are a bit more likely to make it through bad times. The women whose bodies decide to stop growing earlier, or whose offspring trend toward reduced birth weight that still survives, may end up having more successful pregnancies. Hormonal systems adjust. Growth patterns change. Body plans retune themselves to the new normal. There's another factor too: territory. On continents, large carnivores and large herbivores often need very big home ranges. They wander tens, even hundreds of kilometers to find enough food. On islands, you simply can't do that. The sea is a hard barrier. Smaller animals can parcel the landscape more finely. A valley, a slope, a strip of coastal forest can hold more small-bodied individuals than large-bodied ones before it's depleted. By shrinking, a population of hominins might have been able to maintain more stable numbers, avoiding the sharp crashes that plague large mammals in limited habitats. It doesn't mean small is always better. There are trade-offs. Smaller bodies are in some ways more vulnerable to injury. They may lose heat faster in cold snaps. Smaller brains are cheaper to run, but they also set some limits on raw processing power. The pattern we see in Homo floresiensis, tiny brain volume, but hints of sophisticated internal organization, suggests that evolution was trying to walk a narrow ridge, cut down the overall energy budget, but preserve enough cognitive ability for a tool-using, fire-managing, socially complex life. The island rule helps us think about why such a compromise might have been favored. On Flores, there were no saber-toothed cats to outthink, no vast open plains demanding marathon chases of migrating herds. There were instead smallish forests, patchy clearings, rivers, and ridges. A tempo of life where careful foraging, intimate knowledge of the local terrain, and the efficient use of fire could matter more than long-distance travel or massive body size. When you step back, Homo floresiensis starts to look less like a bizarre outlier and more like a predictable outcome of a particular kind of ecological trap. A hominin lineage marooned on an island subject to the same shrinking pressures as elephants and hippos before them. That doesn't answer everything. It doesn't tell us exactly when they arrived, which ancestor they started from, or how quickly their bodies changed. It doesn't explain why they stabilized around a meter in height instead of even smaller, or how their social lives shaped their evolution. But it gives us a framework. Insular dwarfism isn't a magic spell. It's a summary of lots of small advantages compounding over deep time. Fewer predators, limited calories, smaller territories, a simpler, more closed ecological loop. In that setting, thrift wins, compactness wins, the ability to do more with less wins. Apply that logic to a hominin, and Homo floresiensis is one possible answer. To understand the rest of that answer, though, you have to look more closely at the island itself in their time, not just as an abstract set of evolutionary rules, but as a living, breathing community. The dwarfed elephants browsing in the forests, the giant birds stalking through the clearings, the Komodo dragons sliding through the underbrush, the absences as important as the presences, the big cats that never came, the hyenas that never crossed the water. In that strange cast of neighbors lies the full story of how a tiny human could make a big enough living to last on Flores for hundreds of thousands of years. So let's slow the frame down. You're not looking at a map anymore or a list of species. You're standing quietly at dawn on Pleistocene Flores. The air is heavy, warm, damp, not jungle in every direction, but a patchwork. Pockets of dense forest clinging to slopes and river valleys. Scrubbier, drier woodland on the ridges. Open patches where grasses and low shrubs take over. Lava hills, karst outcrops. Streams that flash into torrents when the rains come and shrink back to clear pools when they don't. And moving through all of this is a cast of animals that, if you met them one by one, might seem familiar. It's the combination that's strange. The most important, at least for a hungry hominin, is the stegodon. On the mainland, stegodons were true heavyweights, elephant relatives with long, low skulls and impressive tusks, browsing their way through forests from India to China. Some stood close to 3 meters at the shoulder, with bodies that could soak up hundreds of kilos of vegetation a day. On Flores, they didn't stay that way. Fossils from the island tell the story of at least 2 different stegodon forms across time. Early on, there are larger, more normal animals. Later, especially in the same layers that give us Homo floresiensis at Liangbua, the bones belong to creatures so reduced that some individuals stood barely a meter tall at the shoulder. Think donkey-sized elephants, with all the same basic anatomy condensed into something almost comical by continental standards. This isn't random. It's the island rule, written in ivory and bone. A full-sized stegodon marooned on Flores would be a walking crisis. Too big for the island's productivity, too hungry for the patchy forests and seasonal clearings, each mouth a demand for leaves and branches that might not grow back fast enough. In bad years, the largest individuals would be the first to starve. Generation after generation, that pressure pushes the whole lineage downward. Calves that grow a little more slowly, adults that top out at a smaller size, individuals with thriftier metabolisms, they're the ones that survive the lean times and leave more descendants. Over tens of thousands of years, elephant on Flores comes to mean something very different from elephant in Java or Borneo. But size isn't the only thing that changes. A dwarf stegodon doesn't just eat less, it lives a different life. It probably ranges over a smaller area, moving between a few core feeding zones, rather than wandering across hundreds of kilometers. Its herds, if they formed herds, would be tighter, more localized. It would respond more quickly to shifts in vegetation, to the opening and closing of forest patches, to the arrival of fire. For Homo floresiensis, that matters. If you're a small-bodied hominin with stone tools and fire, a continental elephant is almost a force of nature, something you scavenge from when lightning or predators bring it down, not something you take on directly. A 1-meter-tall stegodon is something else, still dangerous, still heavy, still capable of killing you with a single misplaced step. But it's also, potentially, prey that falls within the upper edge of what a coordinated group, armed with sharpened stone and courage, could manage. At Liangbua, the bones of stegodons are not just lying where animals happen to die. Many carry cut marks, breakage patterns, and burning that suggest butchery and cooking. Whether Homo floresiensis hunted them outright or specialized in scavenging carcasses and finishing off wounded animals, the association is tight. The dwarf elephants of Flores weren't just part of the scenery, they were part of the menu. They weren't alone. Look up from the forest edge and you might see an enormous bird moving with deliberate heavy steps. This is Leptoptilus robustus, a giant stork. Related to the marabou storks and adjutants that haunt continental rivers and garbage dumps today, but scaled up, around 1.8 meters tall, long-legged, long-beaked, with wings capable of carrying it between clearings, riverbanks, and carcasses. Giant storks sound exotic, but ecologically they make sense. On a continent, the role of top scavenger and medium-sized predator is crowded. Big cats, hyenas, wild dogs, vultures, even crocodiles, all jostling for the same carcasses. On Flores, many of those players never arrive. The gap doesn't stay empty. Birds step into it. A big stork can wade in rivers, snatch fish, seize frogs and small reptiles, raid nests, and, crucially, feed on the remains of larger animals. With a strong bill and a long neck, it can strip flesh from a stegodon leg as easily as from a smaller carcass. It can also be a threat to vulnerable young animals, a newborn stegodon, a ground-nesting bird's chicks, possibly even an unattended hominin child. These are all within the potential reach of a large, opportunistic bird. Other avian oddities round out the picture. Large vulture-like birds, oversized relatives of marabou and adjutants. A sky and canopy layer that, in continental ecosystems, would be only one part of a predator guild, here expanded into something closer to an aerial aristocracy. And then, sliding almost invisibly through the underbrush, is the animal most people associate with this region today, the Komodo dragon, or at least its close relatives. Varanid lizards are already impressive on the mainland. The Komodo lineage, given room and time on islands like Flores, Badar, and Komodo itself, did what small predators so often do in insular settings. They got big, not immediately, not to some fantasy monster scale, but big enough to take down deer-sized prey, to challenge juvenile stegodons, to scavenge and dominate carcasses, to deliver septic bites that turn a single slash into a slow-motion kill. Fossil evidence suggests that on Flores during the time of Homo floresiensis, large varanids, whether identical to modern Komodo dragons or close cousins, were part of the landscape. They were likely the heaviest land predators on the island. No lions, no saber-toothed cats, no hyenas. Just these patient, ambush-based reptiles, waiting near waterholes, slipping along game trails, following the scent of blood. For a hominin, that combination, dwarf elephants, giant storks, big lizards, is a very particular world. Your largest mammal neighbor is the size of a pony. The biggest thing that might try to eat you on land is a reptile 4 times your length. The bold, dark shapes circling overhead are not just decoration. They are competitors at every kill site and potential threats to your young. And there are absences that shape your life just as much. No big cats screaming in the night, no packs of canids running you down in the open, no bears to test your claim to a carcass. Whatever smaller carnivores existed, civets, smaller varanids, birds of prey, they operate on a different scale than the giant continental predators. That missing predator pressure is part of what allows stegodons to shrink, birds to expand into scavenger predator roles, lizards to climb their way to the top of the food chain. It also sets the stage for how Homo floresiensis lives. Think about risk for a moment, as a daily calculation. On a continent, leaving the safety of a cave or thicket to cross open ground can be fatal if lions are watching. You need numbers, weapons, constant vigilance. Large predators force you to group up, to keep moving, to never fully relax in the tall grass. On Flores, the calculus shifts. You still have to worry about ambushes near water, about dragons lurking in the shade, about the sudden rush of a big lizard from a burrow or hollow log. But you don't have to scan every horizon for a sprinting cat or a pack of wolves. Risk is more local, tied to specific places and behaviors. The watering hole at dusk, the carcass where storks and varanids gather, the nest cliffs where big birds ride the thermals. Limited prey options shape you too. The island doesn't have endless herds of antelope, zebra, and wild cattle, sweeping back and forth in predictable migrations. The main large herbivore is stegodon, with some smaller deer-like ungulates, rodents, and whatever pigs or other mammals made it across by chance. If you want meat, your choices are constrained. You can track and harass dwarf stegodon herds, perhaps targeting juveniles or weak individuals. Scavenge from natural deaths and dragon kills, arriving early enough to claim a share, trap and hunt smaller animals, giant rats, birds, reptiles, to fill in the gaps. Each of these strategies carries different risks and rewards. Stegodon-focused foraging might yield big payoffs, a single kill feeding a group for days, but it demands knowledge of herd movements, courage in the face of trampling feet, and the ability to defend your prize from dragons and giant storks. Scavenging is cheaper in effort but riskier in competition. Dragons are already specialized in that niche. You might learn to read their behavior, to trail them at a distance, darting in with stone tools when they briefly withdraw or sleep off a meal, but you are constantly balancing the hunger that pushes you toward the carcass against the danger of getting too close. Small game hunting is steadier, more predictable, but it requires fine-grained knowledge of burrows, nests, seasonal patterns, skills passed down orally, embodied in stories and shared practice. It also means that a lot of your calories come from creatures that are themselves tough, wary, and quick, not from lumbering giants. When you put all of this together, the shrinking hypothesis stops being abstract. It becomes a story about daily survival in this specific, peculiar ecosystem. A big-bodied hominin, with the caloric needs of Homo erectus, has to solve the island's equation one way: big game hunting, or heavy reliance on high-yield resources like large carcasses and rich coastal foods. On Flores, the first option is limited by the small number of stegodons and the intense competition at every kill. The second may have been constrained by coastline topography, seasonal variability, and simple distance from good marine patches. The smaller hominin can play a different game: less energy per body, more individuals supported by the same patch of forest. The ability to make a living off smaller prey, scattered plant resources, and occasional stegodon windfalls, without skating right on the edge of starvation in every lean season. In a world where your top land predator is a dragon, and your main large herbivore has already shrunken to match the island's carrying capacity, it would be surprising if the hominin didn't follow suit. Not because evolution has a plan, but because these are the rules the ecosystem is silently enforcing. If the elephants are dwarfed, the storks are giants, and the lizards are apex predators, a meter-tall human with a modest brain and a light frame is not an anomaly. It's the island's logic written into a primate. To see how that logic shows up in daily life, where they slept, what they cooked, how they shaped stone, you have to move from the forests and clearings into the caves and into the slow, careful work of archaeology. Step into the cave. Liangbua, as we know it from excavation photos, is a wide, high chamber with dripstone pillars and layered sediment like a stack of thin, dusty blankets. As they knew it, it was a sheltered hollow in the hillside, open to breezes, dry enough to sleep in, close enough to water and game trails to be worth returning to. What survives of their presence here is mostly three things: bone, stone, charcoal. The bones tell us who else shared their world: stegodons, giant rats, birds, reptiles. The charcoal hints at fire, at least at burning. And between them, scattered through the layers like punctuation marks in a language we're still learning to read, are the stones. Not just any stones. Most rocks on Flores weather into rounded cobbles, fractured rubble, soft material that flakes in thick, clumsy chunks. The pieces in Liangbua that bear the sharp, angular scars of napping are different. Finer grained, tough enough to hold an edge, often brought from sources some distance away. That's the first clue. To make even the simplest cutting tool, someone had to recognize which stones would work and which would crumble. They had to remember where those stones occurred in the landscape, along a particular riverbed, in a certain outcrop, maybe on a slope half a day's walk from the cave. They had to carry them back, or at least shape them on the spot and carry the useful fragments. This isn't random, it's planning, on a scale that spans days and kilometers. The actual tools, to our eyes, are modest. They're often classified as simple flakes and core tools. You take a cobble or a chunk of suitable rock, the core, and strike it with another stone, a hammer. Pieces fly off. Some of those pieces, the flakes, have razor-sharp edges along one side. Others are thicker, more robust, shaped into crude choppers or scrapers. No elegant spear points with delicate symmetry. No long, standardized blades the way you see in later modern human sites. Nothing that leaps out as technological flourish. But that absence can be misleading. Part of it is just tradition. If your ancestors brought a simple but effective flaking core toolkit to Flores, and that toolkit works for butchering stegodons, cutting plant fiber, scraping hides, and cracking open bones, there isn't much pressure to reinvent everything. On an island where raw material sources may be scattered and limited, simplicity is not a sign of stupidity. It is a way of making sure you can do the job with whatever you have. Part of it is preservation. Organic tools, wooden digging sticks, spear shafts, woven baskets, nets, rarely survive hundreds of thousands of years in tropical caves. The stone tools are the hard, durable tips of a much larger technological iceberg that was probably built mostly out of perishable things. If you imagine their world as only rocks, you shrink them unfairly. Even so, the rocks we do have carry hints of skill. Many flakes from Liangbois and nearby sites show controlled removal. The napper hasn't just bashed at the core randomly. They've struck from specific angles to produce edges of a certain length and curvature. Some cores show multiple flake scars radiating from carefully prepared striking platforms, suggesting at least a basic understanding of how to predict the stone's response. Edges have been rejuvenated. A flake dulled by use isn't thrown away automatically. It's sometimes touched up with a few well-placed strikes to restore sharpness. That's not something you do if you think of tools as single-use accidents. It's something you do when you carry a mental picture of what a good edge should be and how to get it back. There's also the matter of mobility. The distribution of certain stone types implies that at least some tools were carried around the landscape. A good core might be used, then taken to another camp, then used again until little remained. A particularly handy flake could be pocketed in a sling of bark or hide, kept at hand for days or weeks. That means they were not just responding moment to moment. They were anticipating needs, the carcass they might find, the plant that needed cutting, the predator they might confront. And then there is fire. Charcoal in caves can come from many sources. Lightning struck trees that fell and smoldered, natural brush fires that sent smoke drifting into openings. But in Liangbois and other florist sites, the story seems more intimate. Burned bone appears alongside stone tools and hominin remains. Some layers show concentrations of ash and charcoal that look less like the random sprinkle of distant smoke and more like the relics of hearths, localized, repeated burning in the same general spots. Stegodon bones bear not just cut marks but charring, as if they were roasted or at least exposed to flames built by deliberate hands. There are debates, as always. Some researchers argue for clear evidence of controlled fire used by the time of Homo floresiensis. Others are more cautious, pointing out that proving repeated intentional fire-making is difficult, especially in caves where natural fires could occasionally intrude. But if we allow ourselves to consider the most straightforward reading, that these small-bodied hominins could, at minimum, manage and maintain fire when nature provided it, the implications spread through their whole way of life. Fire changes food. Meat from stegodon, giant rats, birds, and reptiles becomes easier to chew and digest. Tough plant materials, roots, tubers, fibrous stems, soften and release more calories. Pathogens are killed. Parasites are reduced. The whole digestive burden lightens, which may matter even more when your body is small and every calorie counts. Fire changes safety. A dragon is less bold at the edge of a glowing, smoky circle than in open dark. Big storks and other nocturnal visitors think twice before approaching a firelit carcass, especially if accompanied by movement and noise. A sleeping hollow, warmed and lit by a communal blaze, is a different place from a cold, black cave mouth. Fire changes time. Without it, daylight is your only real working window. With it, you can stretch the useful hours, but perhaps more importantly, you can create a distinct kind of time after the day's foraging is done. Time for grooming, for teaching, for passing on the knowledge of where the best stone is, where the stegodons cross the river, which hollow logs hide dragons, whether their language was rich or rudimentary, whether their vocal tracts allowed full modern speech or something slightly different. That evening firelight would have been the stage on which culture, however simple, was performed. This brings us to the question that hovers over every mention of Homo floresiensis. How smart were they? Their brains, in raw volume, were small, roughly in the range of a modern chimpanzee's, far below Homo sapiens and even below many Homo erectus individuals. It's tempting to see that number and draw a straight line from size to capacity, from volume to intelligence. But brain size is only part of the story. If their lineage came from a larger-brained ancestor that shrank on the island, brain tissue may have been under strong selection pressure to do more with less. Neural organization could have been refined. Regions devoted to vision, motor control, spatial mapping, and social cognition might have been differently balanced than in us. We don't have fossilized wiring diagrams. We only have behaviors inferred from stones and bones. Those behaviors, limited as the record is, point to minds capable of recognizing and selecting specific raw materials in a varied landscape, planning movements, and carrying tools between locations days apart, coordinating group activities around dangerous prey and carcasses, using fire at least opportunistically in ways that enhance safety and diet, maintaining a stable technological tradition over tens of thousands of years. None of this requires them to think like us. It simply anchors them firmly in the realm of purposeful, learning-driven creatures who pass skills from one generation to the next. Think for a moment about how those skills might unfold across a single, ordinary day. Dawn. The cave mouth is gray and cool. A few embers from last night are still faintly glowing under a blanket of ash. One or two adults crouch near them, blowing gently, feeding in dry twigs, coaxing the red back into open flame. A child watches, close but not too close, learning without needing words for oxygen or combustion. Others are waking, bodies small, compact, limbs a little short by our standards, but well suited to climbing, scrambling over rocks, moving quickly through undergrowth. A foraging party forms. 2 or 3 adults, an adolescent, maybe a child old enough to keep up. Each takes something, a favorite flake tucked into a woven belt, a heavier core to be worked later, a wooden stick hardened in the previous night's fire pointed at one end. They follow a narrow path down from the cave, feet remembering each root and stone. Their destination is a patch of forest near a stream. Here, one adult knows, a cluster of stegodons has been feeding. Not huge herds, small tight family groups visiting the same clearings and waterholes, leaving tracks and dung and broken branches. The hominins are not going to try to bring one down today. That would take more people, more coordination, maybe the fortunate moment of a trapped or injured animal. But where stegodons feed, other things happen. Dragons linger in the shade, waiting. Birds patrol the edges, scanning for scraps, for hatchlings, for anything edible. Smaller animals move in the underbrush, drawn by disturbed soil and fallen fruit. It's a node in the island's network of energy flow. The foragers stop before the last screen of foliage. They listen, smell. One climbs a low tree to get a better view, fingers and toes working deftly on the bark. Below, another kneels by a patch of good stone. They visited this outcrop before. The texture under their hands tells them which pieces will fracture well. A few quiet strikes, a decent flake, a core with fresh angles. The new edge is tested on a strip of bark. Satisfied, the toolmaker tucks it away. Later in the morning, farther downstream, they find what they were really hoping for. The smell hits first, then flies, then the quiet side-to-side sway of a dragon's tail. A stegodon calf has died, perhaps injured days ago, perhaps sick. The dragon has already fed, jaws and neck smeared dark. Other smaller reptiles keep their distance. A pair of giant storks stands a little way off, patient, knowing there will be more when the lizard withdraws to rest. The hominins wait too. They don't charge in. They watch the dragon's breathing, the way it shifts its weight. They know, from bitter experience or inherited caution, how fast it can move when it decides to. Finally, the big lizard lumbers toward shade, belly heavy. This is the opening. 2 adults move to the carcass, tools in hand. Another keeps an eye on the dragon. The adolescent, heart pounding, stays back with the child, ready to scramble up the nearest tree if anything changes. The stone edge bites into hide. It's not smooth work. They have to saw, press, use their body weight. But the flake's thin profile makes it possible. Skin parts, warmth and smell rush out. They work quickly, following seams of fat and muscle, freeing chunks they can carry. Bones too big to move are cracked where they can be cracked. Marrow is scooped and smeared on hands and mouths. Stalks edge closer, only to be driven back with shouts, thrown clods, brandish sticks. They don't get everything. They never do. The dragon will come back, the birds will feast, insects and microbes will take what's left. But by knowing when and how to approach, by being willing to share space with dangerous competitors, the hominins convert someone else's kill into calories for their own small bodies. By late afternoon, they're climbing back toward the cave, strips of meat hanging from hands and slung over shoulders, a few new flakes tucked away. Perhaps a mental note of where a promising root patch was seen, or where a dragon burrow lies to be avoided. Evening gathers. Fire flares again at the cave mouth. Meat hisses and smokes. Children watch the sparks trace patterns in the ash. An adult retouches a tool edge. The rhythm of stone on stone is familiar to them as the tap of a keyboard is to us. In that circle of light, under that low, soot-darkened ceiling, the shrinking of bodies and brains that puzzles us doesn't feel like loss. It feels like fit. They are not failed giants, not broken versions of some continental ideal. They are the minds and hands that this island, with its dragons and dwarf elephants and giant birds, has called forth. The tools are rough. The fires are small. The cleverness is quiet, practical, embodied. But it is enough. To understand who they were, you have to ask the question their bones can't answer directly. Who are their parents, and their parents' parents? Where did a 3-foot-tall hominin on a remote island come from in the first place? Right now, there are two main stories on the table. Both are plausible. Both are incomplete. Both lean heavily on a fossil record that looks less like a neat family tree and more like a handful of scattered twigs. The first story says they were descended from Homo erectus. That's the big one. The world traveler. Tall, long-legged, with a brain much larger than any ape's, and a reputation for turning up everywhere from Africa to China to Java. We know erectus reached nearby islands early. Fossils from Java, just to the west of Flores, go back well over 1 million years. Stone tools on some Flores sites are just as old. On this telling, some small group of erectus, maybe carried by currents, maybe blown off course on storm-tangled vegetation, maybe deliberately hugging the coast in simple watercraft, made it to Flores. They arrived with the same basic anatomy as their continental cousins, relatively tall, relatively big-brained, already quite capable. Then the island started to work on them. The second story says, no, they came from something earlier, something that was already small, maybe from a lineage closer to Homo habilis or even late Australopithecines, those shorter, more primitive hominins that walked and climbed their way through African landscapes long before erectus took over. On this view, Flores doesn't have a shrunken version of a large-bodied pioneer. It has a preserved relic of a much older, more archaic body plan that vanished everywhere else. To see why serious scientists can disagree so deeply, you have to look at the evidence they're both staring at, often from opposite angles: bones, tools, and time. Start with anatomy. Homo floresiensis has a strange mix of traits. Some parts of their skeleton look surprisingly advanced, fitting comfortably into the broader Homo pattern. Others look, frankly, ancient. Their feet, for example, are long relative to their legs, with a shape that suggests a different gait from ours, still bipedal, still walking on 2 legs as a normal mode, but with a slightly awkward, shuffling stride. Their wrists and shoulders have features that remind some researchers of much older hominins, less like erectus and more like early Homo or even Australopithecus. The shape of the pelvis, the curve of certain arm bones, the proportions of the face, all these details can be read as throwbacks. That's fuel for the ancient small-bodied lineage camp. They point to those primitive-looking joints and say, you don't get this from simply shrinking Homo erectus. Shrink a big, modern-style human, and you usually get a scaled-down version with mostly the same proportions. Here, they argue, the proportions themselves look different, as if they were never modern to begin with. On the other side, proponents of the erectus ancestor idea push back. They point out that evolution under strong constraints, like those on a small, isolated island with limited food, doesn't always produce neatly scaled-down versions of the original form. When bodies shrink, different parts can change at different rates. Joints, if you picture an erectus ancestor with a relatively large brain, then imagine that lineage getting stuck on an island with limited resources for hundreds of thousands of years. It isn't crazy to think the brain might shrink. Brains are expensive. They demand constant energy. On an island where you don't need to run marathon distances, where giant predators are rare, and where your daily life revolves around a relatively bounded landscape, selection might favor brains that are just big enough and no more. Supporters of the erectus origin model argue exactly that. Start with a big-bodied, big-brained ancestor, compress it through long-term island dwarfism, and you can explain a small body and small brain without invoking a totally different lineage. Those who prefer the ancient relic story look at the same brain size and say, But this fits just as well with an older, small-brained form that never got big in the first place. Why assume shrinkage when you could be seeing persistence? Anatomy, then, can be read in two directions. It's like a script smudged in the middle. Both groups of readers fill in the missing words differently. Next, the tools. On Flores, the stone tools associated with Homo floresiensis are simple. Flake and core technology. Unstandardized shapes. No delicate, elongated blades. Nothing clearly like the more advanced tool traditions associated with late Homo erectus, Neanderthals, or modern humans. This simplicity could be comforting to those who see them as descendants of an older, more primitive hominin. If their tool-making never advanced beyond basic flaking, maybe that's because their ancestors were, from the beginning, on a simpler technological path. But again, the island complicates things. If Erectus reached Flores around 1 million years ago, or even earlier, and then saw their numbers dwindle, their groups fragment, their access to good stone shift with landslides and sea level changes, their cultural traditions could easily stagnate or even regress. Advanced techniques can disappear if the few people who know them die without passing them on, or if the ecological context that made them useful changes. In other words, a simple toolkit on a remote island does not require simple minds, nor does it firmly trace back to a simple-minded ancestor. It might just reflect a long isolated history where good enough was good enough, and where the range of tasks never demanded the flourishing of more elaborate stone technologies. Moreover, the earliest tools on Flores, the ones predating Homo floresiensis by hundreds of thousands of years, are also simple. That consistency over time can be spun two ways. Either it's an old, conservative tradition brought by an archaic ancestor and never replaced, or it's the stripped-down, efficient descendant of a once richer Erectus toolkit, pared away by generations of insular living. Then there's timing. The dates for Homo floresiensis themselves cluster, for now, between roughly 100,000 and 50,000 years ago, depending on the site and the layer. But stone tools on Flores go back far further, to almost 1 million years in some interpretations. If you want an Erectus ancestor, those older tools are convenient. You can imagine early Homo erectus, or a close relative reaching Flores near the start of that long timeline, then slowly changing, shrinking, adapting, until, many hundreds of thousands of years later, they're descendants of the small-bodied beings we call Homo floresiensis. If you prefer a more ancient, small-bodied lineage, you can place that ancestor's arrival even earlier, perhaps before Erectus had fully spread out. You then have to imagine that this older lineage managed something that Erectus later also did, crossing at least one stretch of deep water to reach Flores. That's not impossible, but it adds another layer of uncertainty. And behind all of this, looming like a quiet warning, is the truth that our fossil sample is tiny. A few partial skeletons, a few jaws and isolated bones from other sites, a scattering of tools, a handful of dates, some of which are revised every few years as methods improve and sediments are reanalyzed. An island's deep past is a story told from whatever survives the flood, the landslide, the soil chemistry. Most bones dissolve, crumble, are eaten or scattered. Most sites are never exposed. Of the ones that are, only a few are found. Of the few that are found, only a fraction are excavated before they erode away. When we draw sweeping family trees from this, we're doing something brave and necessary, but also fragile. Almost every neat origin story in human evolution has at some point been overturned by a single new discovery. A skull in the wrong place, a jaw that's too old or too young, a tool in a layer that forces a rethink. Flores is unlikely to be an exception. So what would count as stronger evidence? What would help us say, with a little more confidence, who these islanders descended from? Older fossils, for one. If we found hominin bones on Flores or on neighboring islands that clearly belonged to Homo erectus, securely dated to the earliest tool-bearing layers, that would bolster the Erectus ancestor model, especially if we could see, across a sequence of layers, a gradual trend, tall, large-brained bodies giving way over time to shorter, lighter ones. Alternatively, if we unearthed even older hominin remains with strongly primitive features, more like early Homo or Australopithecus, associated with Flores-like tools, that would lend weight to the ancient relic story. It would show that a small-bodied, archaic lineage really did roam beyond Africa, and survive long enough to leave descendants in the island world of Southeast Asia. Clearer dates would help too. Many of the key layers at Liangbois and other sites have error bars, age ranges rather than precise years. Narrowing those ranges through improved dating techniques, better stratigraphic control, and cross-checks between different methods would let us line up events more confidently. Did stone tools appear on Flores exactly when Erectus appears in nearby Java? Did changes in tool style coincide with climatic shifts or sea level changes that could have isolated populations? Each clarified date tightens or loosens the story's threads. More sites matter as well. Right now, much of what we infer about Homo floresiensis comes from one cave and a few additional locations. More caves, more open-air sites, more coastal deposits. Each could add a slightly different snapshot, a different season, a different phase of their history, perhaps even a different branch of their family. Finally, ancient DNA, if it could be recovered, would be a revelation. In tropical climates, DNA breaks down fast, so expectations are low. But if, by luck or unusual preservation, a fragment of genetic material survived in a tooth or a dense piece of bone, it could instantly show where on the human family tree these islanders fit. Closer to Erectus, off on their own branch near the base of Homo, something else entirely. Until then, we live with ambiguity. What we can say, gently, is this. Whether they came from tall Homo erectus ancestors who shrank on Flores, or from an older, smaller lineage that somehow wandered far from its original home, the island finished the job. Over immense spans of time, through countless births and deaths, through droughts and eruptions and shifts in sea level, natural selection chipped away at their bodies, pared down their brains, honed their behaviors, until the hominins who stood at the cave mouth tending their fires and their tools fit their island as tightly as a key in a well-worn lock. Their origin story, in the end, might not be one clean line back to a single ancestor species. It might be a tangle, with threads from multiple populations mixed and remixed by chance and geography, before being funneled into Flores's narrow evolutionary corridor. For now, we lie here with unanswered questions. Somewhere under layers of volcanic ash, under jungle soil and coral sand, their earlier bones are sleeping. When and if we wake them, our tidy diagrams will shift again. The island has already taught us that bodies can shrink and still carry complex minds. It may yet teach us that our favorite family trees are only drafts. To untangle who they were, we keep running into the same quiet obstacle. Time. Not time in the abstract, but time as it is recorded in dirt and stone. Time as it settles in layers on the floor of a cave, and gets stirred, eroded, and rearranged by water, by gravity, by roots, by pores and bare feet. When you hear that Homo floresiensis lived from about 100,000 to 50,000 years ago, it sounds so clean. 2 numbers, a neat bracket. But those numbers are the end of a long, messy process. They're the labels on a filing system that nature did not design for us. Imagine a cave like Liangbois, where the first hobbit bones were found. It's easy to picture it as a stack of pancakes. The oldest layer at the bottom, youngest at the top, everything in order. You dig down, you go back in time. Simple. Real caves don't work like that. Sometimes the roof collapses and dumps chunks of old rock into younger sediments. Sometimes a flood rushes through, scooping up older material from deeper in the cave and dumping it higher up. Sometimes animals dig burrows. Sometimes humans dig hearths, pits, or graves, shifting sediment from one place to another. Layers can be cut into, sliced, tilted, slumped. Fine ash from a distant volcano might drift in and settle gently, forming a neat horizon. Then, centuries later, a heavy rainstorm might wash part of that ash downhill, mixing it with whatever lies below. Archaeologists have a word for one of their quiet enemies: redeposition. Material that formed or settled in one time and place, then got moved and buried again somewhere else, in a different context, wearing a kind of geological disguise. When the first Homo floresiensis bones were described, the story seemed straightforward. The skeleton known as LB1 came from a layer that, based on the dating methods used at the time, was interpreted as roughly 18,000 years old. That suggested that these tiny hominins were living on Flores astonishingly late, overlapping not just with modern humans in principle, but with modern humans who were already spreading through island Southeast Asia and into Australia. It was a thrilling idea. Also, as later work showed, too simple. As scientists revisited the cave, they realized the stratigraphy, The pattern and sequence of layers was more complicated than originally thought. Some sediments had slumped. Some parts of the cave floor had been disturbed. Material that looked like a single clean layer turned out, under closer inspection, to be a mixture of slightly different deposits. When the dating was redone with better controls and multiple methods, the ages shifted. The bones themselves and the sediments most securely wrapped around them turned out to be far older. Not 18,000 years, more like between about 100,000 and 60,000 years old, with some Homo floresiensis-like material potentially a bit older still. The late surviving hobbit became, in the space of a few studies, an earlier mid-ice age islander. How can the same bone move tens of thousands of years on the timeline? To see that, you need to look at how we actually measure time in places like this. Different dating methods are like different kinds of clocks. Each works best for a certain range and a certain kind of material. Each has its own blind spots. Radiocarbon dating is the one most people have heard of. It measures the decay of radioactive carbon, carbon-14, in once living things, bone, charcoal, shell. As long as an organism is alive, it's taking in carbon-14 from the atmosphere. When it dies, the intake stops, and the carbon-14 already inside begins to decay at a predictable rate. By measuring how much is left, scientists can estimate how long it's been since death. But radiocarbon is a short-lived clock in geological terms. After about 40,000 to 50,000 years, there's so little carbon-14 left that the signal fades into noise. Beyond that, radiocarbon dates get fuzzy, then useless. For much of the time span that matters for Homo floresiensis, radiocarbon is right at the edge of what it can handle, or beyond it. So for older layers, or for sediments that don't contain enough preserved organic material, researchers turn to other clocks. One of these is luminescence dating, often optical or thermoluminescence. The idea is surprisingly gentle. Tiny mineral grains in sand and silt, quartz, feldspar, act like little energy traps. Natural radiation from the surrounding ground slowly charges them, like a battery over time. But if those grains are exposed to bright sunlight, or heated to high temperatures, the trapped energy is released, and the clock is reset to zero. When those grains are then buried in darkness, their energy trap begins to fill again. In the lab, scientists can stimulate those buried grains with light or heat, and measure how much energy is released. That stored signal tells them how long it's been since the grains last saw the sun, or were last heated. How long they've been quietly sitting in the dark. That's what luminescence dating measures, the time since burial. It doesn't tell you directly when a bone in that sediment formed, but it gives you an age for the layer itself. If the bone is clearly embedded in that layer and hasn't been moved, you can link the two. Another family of clocks comes from uranium series dating. Certain minerals, often in cave formations like stalagmites and stalactites, or in some bones and teeth, slowly incorporate uranium from groundwater. Uranium decays into other elements, like thorium, at known rates. By measuring the ratios of uranium to its decay products, scientists can estimate how much time has passed since the mineral formed or the bone started absorbing uranium. Uranium series can reach much further back than radiocarbon, hundreds of thousands of years, but it depends on assumptions about how open or closed the system has been to uranium over time. If uranium seeps in or out later, the clock can be disturbed. There are other methods too: argon-argon dating for volcanic layers, paleomagnetic signatures, correlations with known climate cycles. Each adds another piece to the chronological puzzle. On Flores and at Liangbua, the dating story has been a back-and-forth dance between these different clocks. Early on, some radiocarbon dates on charcoal and other material pointed toward late survival. Then, improved luminescence dating of the sediments themselves suggested many of those charcoal fragments were intrusive, bits that had worked their way down into older layers through cracks and burrows. The sediments around LB1 were older than the youngest bits of charcoal hidden in them. Uranium series dating on some cave formations helped bracket the ages of certain layers from above and below. Volcanic deposits offered anchor points where argon-based methods could be used. As all these strands were woven together, the age estimates for Homo floresiensis stabilized into that older range, roughly between 100,000 and 60,000 years ago, for the main fossil-bearing horizons at Liangbua, with stone tools on the island stretching back much further. But stabilized doesn't mean finished. Every time a new sample is taken, every time methods are refined, the errors bars, the ranges of possible ages shift a little. Sometimes they shrink, sometimes they move. Sometimes a layer that was thought to be continuous turns out to contain a subtle break, a small gap in time. This might sound like technical quibbling, but it has big consequences for the stories we tell. If Homo floresiensis were really still around 18,000 years ago, they would have lived not just alongside modern humans in theory, but in a region where modern humans were building boats, crossing open water, and leaving archaeological traces across the same island chains. In that scenario, overlap and interaction feel almost unavoidable. It invites images of encounters, tall newcomers and tiny islanders meeting on a beach, trading, ignoring each other, or worse. If, instead, the last secure dates for Homo floresiensis are closer to 60,000 or 70,000 years ago, the picture changes. Modern humans were likely already moving through parts of island Southeast Asia then, but the window of potential contact narrows. Maybe they overlapped on Flores for a little while, maybe not. Maybe they passed like ships in the night, separated by a few thousand years. Nothing in geological terms, everything in human terms. These timelines also matter for extinction scenarios. If the hobbits vanish long before modern humans show up in the region, then we have to look harder at other causes: climate shifts, volcanic eruptions, ecological changes, disease, the arrival or disappearance of key prey animals like the pygmy stegodons. If their disappearance seems to line up more tightly with the arrival of Homo sapiens, then human competition, hunting, or indirect ecological impact become harder to ignore as possible culprits. Right now, the safest place to rest is somewhere in between. The best supported dates suggest that Homo floresiensis was gone, at least from Liangbua, by around 50,000 to 60,000 years ago. Modern humans were moving through nearby regions around that same time. Whether their paths crossed directly on Flores, and how long that overlap might have been, remains uncertain. And that uncertainty is not a failure. It's part of what careful interpretation looks like. When scientists talk about the age of a layer or a fossil, they rarely mean a single exact year. They mean a range. Between about 70,000 and 60,000 years ago. No younger than 50,000. Probably not older than 100,000. Those ranges are shaped by the limits of the methods, the quality of the samples, the clarity of the stratigraphy. They're cross-checked by comparing different dating techniques, by looking for consistency between sites, by matching geological events across wider regions. In the case of Flores, some things are now relatively firm. We can say that hominins, some kind of tool-using human or human relative, were present on the island close to 1 million years ago, based on simple stone tools found in older deposits at sites like Mataminga and elsewhere. We can say that by around 100,000 years ago, small-bodied hominins with the distinctive anatomy we call Homo floresiensis were living at Liangbua, leaving behind bones and tools. We can say that, as far as current evidence shows, those hominins disappear from the Liangbua record by around 50,000 to 60,000 years ago, even though the cave continues to be used by other occupants later. We can say that the dating work is still ongoing, that new sites could stretch those ranges, tighten them, or complicate them. Beyond that, we step onto softer ground. Did Homo floresiensis and Homo sapiens share the island for generations, for centuries, or not at all? Were there other refugees on Flores, or on neighboring islands, where hobbit-like populations lingered after they vanished from Liangbua? Could some of the younger-looking stone tools on the island belong to their very last descendants? Or are they all the work of modern humans? Those are questions where the answers are still provisional. They live in the space between sediment grains, in layers that haven't yet been found or properly dated. If you listen carefully, the shifting dates at Liangbua are telling us something humbling. They remind us that nature's archive is messy, that caves are not orderly time capsules but living spaces, burrowed, flooded, burned in, dug out, that our methods, while powerful, have limits, and that confidence grows slowly as independent lines of evidence converge. They also remind us that even small changes in the timeline can flip entire narratives. Move a bone up or down by 20,000 years, and a meeting between species becomes a near miss. A quiet climate fluctuation becomes a lethal stress. A human arrival goes from cause to coincidence. On Flores, the story of the shrinking islanders is carved not just into bone, but into the fine print of mud and ash and mineral grains. It is a story that will keep changing as our clocks get better and our maps of the cave get clearer. For now, lying here with the lights low, it might be enough to hold two ideas at once. First, Some pieces of the timeline are solid enough to lean on. The hobbits were real. They were there. They lived on Flores for a very long time and were gone, at least from the sites we know best, by around 50,000 to 60,000 years ago. Second, the edges of that story, the first footsteps onto the island, the final embers of the last half, are still blurred. The years may keep shifting, but the core remains, a small population in a complicated landscape, leaving traces in a cave whose layers remember more than they are ready yet to clearly say. And just beyond that blurred edge lies one more question, perhaps the most haunting of all. When their time finally ended, how did it happen, and who, if anyone, was there to see it? That's where we go next. Imagine the island in those last tens of thousands of years. Flores is still Flores. Steep green slopes, river valleys, limestone hills riddled with caves. Komodo dragons patrol the clearings. Pygmy stegodons browse in the forests, pushing through undergrowth, snapping saplings underfoot. In the half-dark of Liangbua and other shelters we haven't yet found, small fires burn, smoke curling up toward ceilings already darkened by centuries of soot. Somewhere in that window between about 100,000 and 60,000 years ago, Homo floresiensis is unquestionably here. Tiny bodies, strange heads, clever hands. They are butchering stegodons, shaping stone, tending flames. After that, the record thins and then stops. At almost exactly the same time, a different kind of human is moving through the broader region. Tall, long-limbed, with faces and brains that, if you saw them in modern clothes, you might not look at twice. Early Homo sapiens carrying with them a history forged in African bottlenecks, language-rich societies, and tool traditions that can leap from group to group like sparks on the wind. Did those tall newcomers ever stand face to face with the island's small ancient residents? The honest answer, as far as the evidence goes, is maybe. And maybe here is not a shrug. It's a narrow passage between what we know and what we don't. The timings, as they currently stand, line up just enough to make contact possible. Modern humans were moving through parts of island Southeast Asia by around 50,000 to 60,000 years ago, maybe earlier. The last secure traces of Homo floresiensis at Liangbua fall into roughly that same span. But we don't yet have a layer where the bones of both species sit together in the same undisturbed sediment, or a tool that can be tied with certainty to one group and then found clearly overlain by the other. So, we are left with scenarios. In one, there is real overlap. A modern human group reaches Flores while hobbit populations still occupy parts of the island. The two lineages, separated by hundreds of thousands of years of evolution, meet on a beach, or at a river crossing, or in the shadow of a cave mouth. Perhaps they watch each other from a distance. Perhaps they ignore each other. Perhaps something more complicated happens. Cautious exchanges, shared kills, or, at the other extreme, conflict. In another scenario, they miss each other completely. The last Homo floresiensis dies out on Flores centuries or millennia before the first Homo sapiens canoe noses up onto its shore. To the newcomers, the island is empty of other humans, populated only by strange animals and the already fading traces of an earlier occupation they do not recognize and have no way to name. Right now, the data can't rule either picture out. What we can do is look at what tends to happen when small, isolated populations are pushed, and when new, more numerous groups arrive in their worlds. Homo floresiensis, as far as we can tell, was never a species with big numbers. The entire island is not that large, and island ecosystems put hard ceilings on population size. Fewer large animals to hunt, fewer plants to harvest, fewer safe breeding places, maybe a few thousand individuals in total at their peak, maybe fewer. Whatever the exact figure, it would not have taken much to destabilize them. Small scattered populations live with a kind of constant mathematical bad luck. If you start with only a few hundred breeding adults, you don't need many lean years in a row for birth rates to dip and death rates to rise. A disease that kills just a portion of the children, a couple of failed rainy seasons that make food scarce, a volcanic eruption that wipes out one key valley. Each shock chips away at the number of surviving adults. At some point, even if the environment recovers, the population may be too small and too fragmented to bounce back. Geneticists call some of these risks demographic stochasticity and genetic drift, but you can think of them in simpler terms. In a big population, there are buffers. If one group has a bad year, another group somewhere else might have a good one, and the overall numbers smooth out. In a small population, there are no such cushions. A few unlucky coin flips in a row and whole family lines disappear forever. On an island like Flores, those vulnerabilities are turned up to full volume. There is nowhere else to go, no neighboring continent from which new migrants can arrive to refill the gene pool. If one valley's stegodons vanish, there is no great herd waiting over the horizon to wander in and replace them. Now fold into that fragility the kinds of forces we know were at work in the region. Climate was not standing still. Over the period when Homo floresiensis lived and vanished, global ice sheets advanced and retreated. Sea levels fell and rose, rainfall patterns shifted. In some phases, Flores was likely cooler and drier than today. Rivers would have shrunk or shifted their courses. Forests might have thinned into drier woodland or grassland in some areas, then closed in again in others. Pygmy stegodons, those essential sources of meat, bone, and fat, seem to disappear from the Lianghua record roughly when the hobbits do. Whether that's cause or effect is still being worked out, but it's easy to see how a change in the stegodons' fortunes could cascade. If a combination of climate change, volcanic ash, or disease hit stegodon populations hard, hunting would have become less reliable. A species tailored over hundreds of thousands of years to a particular island menu, small elephants, particular plants, certain reptiles and birds, might find itself suddenly mismatched to what the land could provide. Volcanoes were part of this story too. The islands of Indonesia sit along a restless geological boundary. Ash layers in the region testify to eruptions big and small. Ash doesn't just drift gently onto roofs and leaves everything else the same. A thick fall can smother vegetation, poison water, alter river courses, and temporarily strip landscapes of food for grazers and browsers. Stegodons weakened by ash-choked pastures might fall to disease. Predators and scavengers, including hominins, might suffer in the aftermath. Sometimes extinction is not a single dramatic blow. Sometimes it is a staircase of small steps downward. A bad decade here, a lost hunting ground there, a disease that moves through a too small population, picking off key individuals. Perhaps a local group at one end of the island dies out, leaving a gap. The remaining groups are now farther apart, their ability to exchange mates and information reduced. Vulnerability creeps upward, quietly. If modern humans did arrive before the final step on that staircase, they would have added new pressures, even without meaning to. Homo sapiens coming down the island chains with more advanced projectile weapons, denser social networks, and flexible diets, tended to make a big ecological footprint wherever they went. They hunted efficiently. They burned vegetation to clear paths and encouraged certain plants. They introduced new fire regimes, even if they never deliberately targeted Homo floresiensis. Their arrival could have changed the balance, competing for the same prey, altering habitats, disturbing sleeping sites, bringing in new diseases to which the hobbits had no defenses. There is no firm evidence yet that this happened on Flores. No kill sites where hobbit bones lie mixed with sapiens tools. No clear-cut layer where we can say, here, this is where the tall ones arrived and the small ones vanished. But from other parts of the world, from Australia to the Americas to islands in the Pacific, we know that when humans, with our technological and social package, step into long isolated ecosystems, extinctions often follow within a few thousand years. It may be that on Flores, several threads tangled together. A changing climate that subtly shifted plant communities, volcanic episodes that periodically scarred the landscape, the decline of stegodons and other key animals, the inherent fragility of a small-bodied, small-numbered population trapped on a single island, and layered on top the eventual arrival of modern humans with their own needs, fires, and hunting strategies. Against that background, extinction need not be sudden or cinematic. There is no requirement that the last Homo floresiensis dies in some great final confrontation. The end could have come in ways that left almost no trace. You can imagine the last centuries as a soft dimming rather than a sharp cutoff. A few valleys where hobbit bands still hunt stegodons and gather roots, even as numbers shrink. Births a little rarer, child mortality a little higher. A storm that wipes out a crucial stand of fruiting trees. Disease that takes too many adults in one bad season. A fall from a cliff that removes a skilled hunter whose knowledge no one quite replaces. At some point, a child is born who will never meet anyone smaller than herself, because her parents are the last of their group. At some point, the last fertile pair fails to have surviving offspring. They live out their days hunting and gathering as their ancestors did. unaware that every path they walk will soon be unwalked by anyone like them. When they're gone, the island is quiet about it. Bones decay. Some are carried off by animals. Some lie on open ground, exposed to sun and rain and roots. Only the rarest are sheltered by just the right conditions in a cave, entombed in sediment that won't be washed away, crushed, or dissolved. Of those, only a handful will ever be reached by human hands with trowels and brushes tens of thousands of years later. A species can exist for hundreds of thousands of years and leave behind only a few partial skeletons in a single cave, a scatter of tools in a couple of stream beds, and a gap in the bones of its prey. That is not failure on their part. It is just how time works. Most of what lives is not remembered in detail. On Flores, Homo floresiensis seems to have faded in this quiet way. No signatures of massacre. No clear sign of a single catastrophic event that erased them overnight. Just a thinning out of traces in the layers, an end to their particular style of tools. A silence where stegodon bones once lay cracked and burned. Whether modern humans ever watched that fading from nearby, or whether they arrived to find only ghosts in the sediments, we do not yet know. What we can say is that by the time later peoples were moving through Liangbua, decorating its walls with smoke, lighting new hearths in old hollows, the small islanders who first used that cave were already long gone. Still, the island may have remembered them in other ways. Stories told around later fires about little people in the hills, shapes glimpsed at the edge of vision, rumors of hidden valleys where small footprints were once seen. Folklore is not a fossil record, but sometimes, faintly, it can echo older presences. In the last part of this journey, we'll step out of the deep timeline and listen to those echoes. The tales that modern inhabitants of Flores and neighboring islands tell about small folk in the forests, and what those lingering whispers might reveal and conceal about a species that shrank, survived, and finally slipped from the living world almost without a sound. Begin for a moment, not with bones, but with stories. Long after Homo floresiensis disappeared from the sediments of Liangbua, other humans were living on Flores, farming, fishing, moving up and down the valleys, sleeping in houses instead of caves. And like humans everywhere, they told tales. In the mountains and forests of Flores, one of those tales speaks of the Ibu-Gogo. Depending on who is telling it, the Ibu-Gogo are small people, or not quite people, who live deep in the hills. They are said to be short, with broad faces and long hair, sometimes pot-bellied, sometimes wiry. They can talk, but only poorly, mimicking human speech in a way that never sounds quite right. In some versions, they sneak into villages to steal food, especially crops and small animals. In others, they carry off human children. They are clever, but not wise, tricky, but not invincible. They are, in other words, the sort of beings who show up in folklore all over the world. Little wild folk who live just beyond the edge of the cultivated world. Not fully animal, not fully human. Troubling and fascinating at the same time. When news of Homo floresiensis reached the wider world in the early 2000s, it did not take long for people to make a connection. Here, in a cave on Flores, were the bones of a small-bodied human relative. Here, in the living traditions of Flores, were stories of small-bodied forest dwellers. Was this, some wondered, cultural memory? A distant oral echo of a time when two kinds of humans really did share the island? It is an enticing idea. Our minds are drawn to links like this, bones and stories lining up neatly across tens of thousands of years. A people remembered not by name, but as the little ones in the hills. And yet, this is where we have to move carefully. Folklore is not the same thing as a fossil record. Stories do not come with radiocarbon dates. They evolve, just as species do, picking up new details, dropping old ones, blending with neighboring tales as people move and intermarry. The Ibu-Gogo of one valley might not be quite the same as the Ibu-Gogo of another. The version told to an anthropologist in the 20th century may already be the product of centuries of change. Small, strange beings in the forest are an almost universal human theme. Europe has its elves and brownies. The Philippines has its duende. Many indigenous traditions in Australia and the Americas speak of little people, who can help or harm, who live in caves, trees, or stone circles. You do not need a fossil species to explain the appearance of such figures. All you need is a border between the known and the unknown, a dark forest, a misty mountain, a cave mouth at dusk. So, on one side, we have a tempting story. that memories of real encounters with Homo floresiensis survived in oral tradition for tens of thousands of years, reframed as myth, but still preserving a kernel of historical truth. On the other side, we have the sober limits of evidence. No direct datable link between particular tales and particular hominin species. No way yet to trace a clear line from a hobbit skull in Liangbua to an Ebogogo whispered about in a 21st century village. Where does that leave us? Somewhere in between, in a space where respect and caution have to sit side by side. Respect, because these stories matter to the people who tell them. They are not just curiosities for outside researchers to mine for clues. They are part of living cultures, woven into ideas about landscape, morality, danger, and belonging. To treat them only as potential data points about extinct species is to flatten them into something they are not. Caution, because it is easy for outside imaginations to run away with themselves. To say, the locals knew all along, as if that settles a scientific question. Or worse, to use folklore as a kind of decorative proof, a way to dramatize a narrative that the bones themselves do not fully support. A more grounded way to think about it is this. Islands, with their thick forests and steep mountains, almost invite tales about others who might be there. When you live in a place where there are real caves you have never entered, real valleys you have never walked, your mind populates them. With spirits, with ancestors, with small people who were here before you. Whether or not any particular myth preserves a memory of Homo floresiensis, the very persistence of small people in the hills stories tells us something human. It tells us that we are uncomfortable with the idea that land is ever completely empty. We prefer to imagine prior claimants, hidden neighbors, old presences just out of sight. And this is where Homo floresiensis changes things, even if folklore never led us to them. Before their discovery, our picture of recent human diversity was narrower. By around 50,000 years ago, many researchers imagined a world with just a few hominin players left on the stage. Neanderthals in Europe and Western Asia, Denisovans somewhere to the east, and Homo sapiens spreading out of Africa and across the globe. Island Southeast Asia in this view was mainly a corridor, a place our species passed through on the way to Australia and New Guinea. The bones at Liangbua cracked that picture open. Here was evidence that, tucked away on a single island, another hominin lineage had persisted deep into the late Pleistocene, not a slightly different sapiens group, not a recent cousin like Neanderthals, a form that, in some anatomical respects, looked more like much older humans, yet was making tools and using fire in an environment shaped by modern climates and modern humans moving nearby. Homo floresiensis told us that the late Pleistocene was not a simple handoff from archaic to modern. It was a braided, tangled period in which multiple human kinds, some very ancient in their roots, could survive in parallel, especially in isolated refuges. Once you accept that on Flores, you have to consider that it might have happened elsewhere. Are there other islands in Southeast Asia that once held their own small or unusual hominins? Places where steep terrain, limited resources, and long isolation shaped bodies and behaviors in ways we have not yet seen. Sulawesi, Timor, even remote parts of Borneo and the Philippines. These all sit in the same kind of geological and ecological theater. And yet, finding more hobbits is not as simple as going out with a shovel. DNA, the tool that has revolutionized our understanding of Neanderthals and Denisovans, has so far been silent on Flores. The tropics are rough on genetic material. Heat, were hobbits the descendants of an early wave of Homo erectus that shrank on the island? Or do they come from an even older dispersal of small-bodied hominins, relatives of species like Homo habilis, carrying a very ancient body plan into a very modern time? Was there gene flow between them and other humans? Or were they already too far gone down their own evolutionary path to interbreed? Are the Liangbua individuals the last of their kind, or just the last ones we have found? Could older or younger fossils be sitting, unrecognized, in other caves, in other layers, waiting for a landslide or a road cut, or a careful survey to expose them? Even the timeline we have is slippery. Each new dating technique, each re-examination of sediment layers, has the potential to shift their appearance and disappearance by thousands of years. That can make the difference between they were definitely gone before sapiens arrived, and they might have shared this valley for a while. This uncertainty is not a flaw in the story. It is part of what keeps the mystery alive. We have just enough to know that something remarkable happened on Flores. A human lineage reached an island and over long ages became small, specialized, and strange. We do not yet have enough to chart every step in that journey, or to say exactly how it ended. In that sense, Homo floresiensis teaches us two things at once. First, that our family was more varied, more imaginative than we once thought. That as recently as 60,000 or 70,000 years ago, the world held not just us and a couple of close cousins, but islanders whose bodies and brains followed different rules, yet still made fire, tools, and a living in demanding landscapes. Second, that even in an age of satellite maps and global databases, the Earth can still hide entire human stories in the folds of its terrain. A few meters of sediment in a single cave were all that stood between Homo floresiensis and complete oblivion. If those deposits had washed away in a flood, if that cave roof had collapsed differently, we might never have known they existed. Islands make this kind of forgetting more likely and more dramatic. Cut off by water, they become closed laboratories. Species arrive, change, sometimes shrink, sometimes grow, sometimes spin off into forms that make no sense on the mainland. When conditions shift, they can vanish without sending out new migrants to carry their genes elsewhere. Their entire evolutionary experiment begins and ends within the ring of the sea. Flores is one such laboratory. So are dozens of other islands, from the Mediterranean to the Pacific. Each one has run its own quiet trials with elephants, rodents, lizards, birds, and on rare occasions with humans. When we listen to the folklore of these places, the little people, the giants, the spirits of caves and cliffs, we are hearing in part how later inhabitants tried to make sense of living in landscapes shaped by those long experiments. They felt that the island was old, that others had been there before. They filled that sense with names and faces. Science enters with trowels and microscopes and dating methods, peeling back the layers under those stories. It does not confirm the tales in any simple, one-to-one way. But it does reveal that the basic intuition, that islands remember transformations, is not wrong. In the end, the hobbits of Flores are not just a curiosity or a punchline about tiny humans. They are a reminder that isolation can bend even our own lineage into unexpected forms. That being human has never meant just one body shape, one brain size, one way of living. And they are a reminder of how easily such forms can appear, persist for hundreds of thousands of years, and then disappear almost without a trace, leaving behind a few bones in a cave, a gap in the history of an island's animals, and maybe, just maybe, a lingering whisper in the stories told when the lamps are low and the forest outside is very dark. From the outside, that can look like a strange accident on a single remote island. Step back, though, and it fits into a broader pattern. Islands, over and over, take what arrives on their shores and reshape it. Big becomes small, small becomes giant, familiar becomes unfamiliar. Lineages stretch in directions they never would have taken on the open continents. Flores did that with elephants and storks and lizards. It did it, once, with a branch of our own family. In their shrinking and their long endurance, the hobbits show us what islands are always doing, turning isolation into transformation, and then, in their own time, letting those experiments fade back into silence. So, here at the end of the story, let's gather the threads and lay them down gently. A long time ago, sometime around 50,000 BC or earlier, a group of humans, or almost humans, reached an island that did not make things easy for them. Flores was steep, volcanic, cut off by deep water. No wandering herd would accidentally stroll there. However they came, on roughs they didn't quite understand, clinging to storm-tossed vegetation, or through slower movements over shallower channels during lower seas, they arrived as strangers. Then the sea closed around them. What began as a journey ended as confinement. No more easy exits, no more following migrating animals to new valleys. Instead, one island, one set of resources, one set of pressures, and over tens of thousands, maybe hundreds of thousands of years, those pressures did what evolution always does when time and isolation are given room to work. They reshaped a lineage. Big bodies became costly. A large frame needs more food, more water, more safety margins when times are lean. On an island with small forests, limited prey, and no gigantic predators to outrun or fight, the balance tipped. Smaller bodies used fewer calories. Smaller bodies could survive longer in a bad season. Smaller bodies fit better into caves and crevices, could climb and hide and wait. Step by slow step, generation by generation, The tall ancestors who had first reached Flores gave way to their diminished descendants. Brains changed shape, limbs shortened. The skeleton recorded the quiet arithmetic of survival. What we see in Homo floresiensis is that arithmetic written in bone, the island rule applied to our own family. They did not become small to fit into a fairy tale. They became small because on Flores that was a winning strategy. Along the way they did something else. They persisted. They made stone tools suited to the animals they hunted and the plants they processed. They controlled fire in a landscape of sudden downpours and dense vegetation. They lived in an ecosystem of pygmy stegodons, giant storks, and Komodo dragons, threading their lives through a food web that had already been warped by island dynamics. For a very long time, this worked. Long enough that when modern humans finally pushed through island Southeast Asia, the hobbits had already survived more volcanic eruptions, more sea level changes, more ecological turnovers than we can easily imagine. And then, quietly, they were gone. Whether modern humans ever met them face to face is still an open question. The dates shift. The lines on our timelines blur and slide past each other. Maybe there was a brief overlap, a shared horizon on the same island. Maybe there was none at all, and their disappearance had more to do with environmental change or the fragile mathematics of small populations than with any direct encounter. Either way, the result is the same. A lineage that had adapted so precisely to one island's demands could not bend any further. When conditions stepped outside the range they were built for, new climates, new competitors, new disturbances, the experiment ended. That might sound sad, but in deep time, this is the rule, not the exception. Species arise, specialize, and vanish. Shorelines move. Rivers cut new paths. Islands appear as volcanoes rise from the sea, then erode back into waves. Whole worlds of plants and animals come and go without leaving any mark we can see from the surface. Homo floresiensis is unusual not because it vanished, but because it left just enough evidence for us to notice. A handful of bones, some tools, a cave with the right depth of sediment, enough to catch the flicker of a small-bodied human lineage that lived, adapted, and disappeared before we ever wrote a word. If you pull back far enough, the story of Flores becomes one frame in a much larger film. Sea levels rising and falling, turning hilltops into islands and islands back into hills. Shorelines sliding miles outward during glacial lows, then creeping back in again as ice melts. Each shift opening and closing pathways for plants, animals, and hominins. Each new configuration of land and sea inviting some lineages to spread and forcing others into corners where they either adapt or fade. Right now, you and I are living on just one version of that map. The coastlines that feel permanent, the islands that seem immovable, are all mid-gesture. Given enough time, today's continents and archipelagos will look as strange to future eyes as the Pleistocene map looks to us. Somewhere under those future shorelines, more caves like Liangbua will sit in the dark, already holding their secrets. That is one of the quiet lessons of a shrinking lineage. How much of the human story lies just beyond what we have managed to notice? One island, one excavation, and a whole new kind of human steps into view. It makes you wonder how many other stories are still sleeping under limestone roofs, or buried in valley floors, or hidden in the sediments of sinkholes we have not yet probed. Even now, with satellites mapping coastlines and databases cataloging fossils, the Earth is still full of places where a trowel has never broken the soil. Full of cliffs and caves that, from a distance, look like any other, but inside might hold the remains of another unexpected cousin. Another experiment in being human that took a different shape, followed a different rule, and then fell silent. As you drift towards sleep, you can imagine the planet in slow motion. Islands rising and sinking, forests spreading and retreating, small bands of humans and near-humans moving along beaches that are now drowned, or camping in caves that now sit high above rivers that have shifted away. Every so often, one of those movements leaves just enough trace for later eyes and later minds to piece together. And every so often, as on Flores, that trace is surprising enough to remind us that our family history is not a straight, well-lit road, but a network of side paths, some broad, some narrow, some ending in tiny, remarkable clearings like the Hobbit's Island. If you'd like to wander further into those side paths, into more prehistoric secrets, more half-buried stories from deep time, I've put many of them into a book. You can read more about it, and pick up a copy if you like, at sleepytimehistory.com. Before you go, if this journey to Flores helped you relax or gave you something gentle to think about as you fall asleep, it really does help if you tap like, leave a comment, and subscribe. Those small actions are what keep this kind of slow, careful storytelling drifting out to new listeners. And if you're still awake enough, I'd love to hear from you in the comments. Where in the world are you listening from? And what time is it right now as you lie there, somewhere on your own piece of this changing planet? For now, you can let the island fade. Let the cave roof close again. Let the little lineage that shrank and endured slip back into darkness. The sea will keep rising and falling. The shorelines will keep moving. And somewhere, under rock and soil and time, more stories are waiting for the day when a careful hand uncovers them, and another quiet voice begins to tell them.